Hello and welcome to a lecture on RLC circuits. So this is sections 21.4 and 21.6, and this represents the second half of lecture 13, where the first half of lecture 13 covered the earlier sections in chapter 21. This is material that will be on exam 2 and introduces the idea of a alternating circuit that has a resistor, that's the R, an inductor, and a capacitor. So one of each. Okay, so in this lecture we're going to introduce some key terms, look at some new equations, and do some simple examples. Our objectives are to learn the basics of an AC circuit that has a resistor, capacitor, and inductor all in series. That is the only orientation of those three circuit elements that we'll be discussing. We're going to understand how the concept of a phasor helps us understand the total voltage in an RLC circuit, as well as the total impedance on the current. Impedance being a term that we'll define, but it's what you might think. It represents the current being slowed down or choked. We're going to understand how the concept of phasors allows us to calculate the phase angle of an RLC circuit and use that angle to find the power factor and the average power output of the circuit. So the phase angle is something that we'll discuss quite a bit. And we're going to learn that the RLC circuits have a resonant frequency that occurs when the reactance of the capacitor is equal to the reactance of the inductor. Reactance being a similar idea as impedance. More on that in a minute. And when that resonant frequency is reached, we have a minimum total impedance and thus a maximum current. So that's our circuit to working at maximum power. Okay, so let's get to discussing some of our key terms here. All right, so the first one is the idea of a phasor and a phasor diagram. So a phasor is simply a rotating vector. Okay, so it has all of the same properties of a vector, namely that it is defined by its length and its angle. And here, the idea is that the vector is going to be rotating at some frequency. Okay, so it's rotating with a frequency of omega, so with angular frequency. Okay, so angular frequency omega. Okay, and a phasor diagram is a XY graph that represents the phasors, so those rotating vectors, and shows the instantaneous values of current and voltage as projections onto the x-axis. All right, so I just need one more line here. So projections onto the x-axis, and that's just a way that the plot is defined. Okay, so let's get to some of the material, make sense of this, because it is an interesting idea, and it's one that you want to make sure that you kind of have a handle on as you get into this topic, because we'll be doing a bit with it, no complicated formulas or long computational problems, but just a concept that on its surface requires a little bit of upfront work. So let's take a look at this first diagram. All these diagrams do a wonderful job of illustrating what a phasor is. So when we look at this first one, zoom in on the bit, we see that we have indeed an XY plot. Okay, so again, all of our instantaneous values of current and voltage are going to be the ones that are projected onto the x-axis. So whatever components we see on the x-axis are going to be our instantaneous values. I won't label that here because it will make more sense when we rotate it in the diagrams below. But what I do want to call particular attention to is an idea that we are building on from the first half of this lecture, so the first half of lecture 13, and those being sections, the earlier sections So, the earlier sections of chapter 21. So what I mean is this. If we look here, we have the voltage of the resistor, which is then defined using Ohm's law as just IR. Okay, and so we notice right away that the voltage of the resistor is in phase with the current. Okay, so we're going to label that here. So the voltage is in phase with the current. And the phase, I really want you to visualize that as a unit circle, okay? Because, unit circle also represented on an XY plot. And so we can really think of going in the direction of the unit circle with positive angles in the counterclockwise direction and negative angles in the counterclockwise direction. In fact, we can put a quick label here that this is the direction of positive theta for rotation. Okay, so first idea then is that the phase shift then between the unshifted voltage of the resistor and the shifted voltage of the inductor is the inductor is pi over 2 or 90 degrees phase shifted ahead of the current. Okay, so here we have the voltage and so voltage of inductor is pi over 2 ahead. Okay, and see the earlier sections of the notes to see how that is consistent with what we wrote back then. And then here I actually want to write voltage of the resistor. Okay, and then we've got our next one, which is the capacitor. So if we look at the phase angle for the capacitor, well, we see then that that voltage is lagging behind the current. Okay, so voltage of capacitor is pi over 2 or 90 degrees behind. Okay, so those are our two angles, right? We've got our two 90-degree angles, one shifted ahead, one shifted behind. That also means that when we look at these two vectors, the vectors that represent the rotating vectors, the phasors for the voltage of the inductor and the voltage of the capacitor respectively, when we look at those, we see that they are exactly out of phase. We have 180 degrees out of phase between those two. So that actually means that they are canceling each other out effectively, okay, at least in terms of their phase. Okay, and definitely more on that in just a minute when we talk about the idea of resonance. Okay, but right now this whole picture here is sure a vector diagram, but the phasor nature isn't really obvious. But it is if we look down below, because we see now we've taken our same vectors, so our current into the circuit, our unphase shifted voltage across the resistor, our shifted ahead voltage across the inductor, and our shifted behind voltage across the capacitor. And we've taken all four of those vectors and we've rotated them because we have an alternating current. So the current is changing in time. The current is varying from max to 0 to negative max. We have a alternating current. And to call memory to that, basically the idea is simply that we have our instantaneous current, often represented as the lowercase I, as a function of time, is then going to be varying in time in something like this. Okay, and so then what we're looking at as we go through time, right, our omega t, is we're shifting it, right? So this value here of t, this value of time, would be less than pi over 2. Right? So, or I should say, it'd be less than a quarter of a period. So we can know that because a quarter of a period would get us all the way to here, because that would be 1/4 of a full rotation. And so, so this would be right here, would be our period uppercase T. All right. So that's what's happening, right? Our current in this case is going from a max value, because that would be on our vertical axis, that would be our I naught, as shown in the figure. That's our maximum current. It's on its way down to 0, right there, 0. But we're not there yet because we haven't rotated all the way over. So how does that get represented in the graph? Well, if we scroll down, we can look at the next one, and we'll clearly see the idea of how we take our maximum value of current and we get our instantaneous value, which here is represented just by I without a subscript. Okay, so let me add a label to that. So this would be our instantaneous current. Instantaneous current. So indeed we see that that projection of the maximum is becoming smaller, all right? And once we go through an entire quarter period, we'll be at this point where the instantaneous current would be 0 because the x projection, this shorter vector here, would become, well, effectively a length of 0. It would be so short it wouldn't exist. Okay? And so that's the idea of the rotating vectors. Okay? So we see just the rotating current. And if that was just the rotating current, it wouldn't be all that helpful because it would certainly kind of show directly that a sinusoidal function of a variable, in this case current, varying over time, goes through a unit circle like so, and that is consistent with this picture up here. But the real utility of the phasor is that now we can have our phase shifted voltage on the inductor, phase shifted voltage on the capacitor, combined with the unphase shifted voltage across the resistor, and take all three of those together and get the total effect of the voltages, right? And really see how all the vectors are moving together. Okay, so what does that mean? Well, let's take a look. So one thing is it's not just the current that is getting projected onto the x-axis. It is also the voltage across the resistor, which is getting projected onto the x-axis as a similar triangle. So a triangle with proportionally equal sides to the current, right? So those two triangles are similar. But what's happening with our other two voltages? Well, we have the voltage across the inductor is getting projected on the x-axis. So that would be instantaneous voltage across the inductor right there. Likewise, the maximum voltage across the capacitor has an instantaneous value. So the instantaneous value of the voltage across the capacitor is the shorter dotted red arrow, this one. Okay? So we can project all of them to get their instantaneous values, right? So now we really see the phasor at work. Now the last step that we can do with our phasor diagram is shown down here, where we've combined the effects of the voltage across the capacitor and the inductor shown here. Okay, so this is the combined voltage across the inductor and capacitor. And why did we combine them in such a way that we subtracted the capacitor from the inductor? Well, because they're always exactly 180 degrees out of phase, or pi radians out of phase. So effectively, the voltage across the capacitor is attempting to cancel out the voltage across the inductor because they're exactly out of phase with each other. And so just like you can have sound waves get canceled or other physical waves get canceled when they're exactly 1/4 of a repetition, so 1/4 of a period, 1/4 of a wavelength out of phase. Okay? So let's see then, we have that effect, okay? So that's the combined effect of the voltages. And then now we have formed, and this is the real crux of it, this was makes this problem the one that we can discuss, one that we can use mathematical tools to work through, is that now we have a right triangle. Because this vector right here, this combined voltage across the inductor and capacitor, is the same vector over there, because the location of the vector doesn't matter. That's not how vectors are defined, but its length and magnitude do. And those two vectors are identical in length and magnitude. So when we look at our VLO minus VCO, so voltage across the inductor here, voltage across the capacitor here, when we look at that side of the triangle, of course what we have is a right triangle right there. And now that we have a right triangle, we can use the equations of the trigonometric equations, so cosine, sine, and especially tangent. We can use the Pythagorean theorem in order to find an expression that hasn't shown up on our diagram so far, but that is the overall voltage of the circuit. Notice, right? Up above, we had all the voltage across each individual component, as well as the instantaneous voltages across each individual component. But this expression right here, this one that I've circled right there, That is a new quantity because that is the overall voltage. Okay, so we can call this the total voltage across RLC circuit. And that's really helpful because now we have an expression that refers to the circuit as a whole. Obviously, a big part of our focus of taking a circuit is trying to find out what it does as a whole by understanding its individual parts. Okay, so last couple things to look at is now that we have that expression, a total, at least that pictorial expression of total voltage across an RLC circuit, we can find its instantaneous value right down here. So this is the instantaneous voltage across the RLC circuit. And again, that's just the projection onto the x-axis. And so we can see then that as we continue to rotate, that projection would, of course, approach 0. And the total voltage is going to be 0 at the same point. That the current is going to be entirely in the y direction. And so the current, they're going to be in phase in that respect. But the actual length of it is going to be is absolutely determined by how big the difference between the voltage across the inductor and the voltage across the capacitor are. Okay, so that, in other words, the something about the capacitor and the inductor matter, and that's going to be the reactance, which was discussed earlier in this lecture. Okay, so let's then just label our last thing here, our instantaneous. Okay, so instantaneous total voltage. Okay, so I hope that makes the ideas of phasors make a little bit more sense. Again, they're not the most intuitive thing, but they ultimately are allowing us to form a right triangle. If you really want the concise definition and what they're effectively doing is a crucial idea, is getting a right triangle so we can use some trigonometric expressions. Okay, so let's get to one of the goals of all of this phasor diagram discussion, and that's understanding the idea of impedance. Okay, so impedance is the total effect of reactances and resistances on a RLC circuit's current. Okay, so really it's serving a very similar role to reactance. We kind of have another word that is synonymous. So what we can say in summary, or kind of an important note here, is that resistance, reactance, and impedance all have units of ohms, because what they're all doing is all three of those ideas, whether it's a resistor's resistance, a capacitor or inductor's reactance, or the total impedance of a RLC circuit, all of those ideas are slowing down the current. So we'll say resistance, reactance, and impedance all have units of ohms, and they can all be used with some version of Ohm's law. Okay. All right, so then last idea here, the phase angle of the RLC series circuit. Okay, so this is described as the angle that is represented by the right triangle was composed in the picture of the total voltage, or the sum of the voltages across the inductor and capacitor on one side of the triangle, and the voltage across the resistor on the other side. Okay, so this is the angle of right triangle formed by the voltage across the inductor minus the voltage across the capacitor and the voltage across the resistor. Okay, and those would be all maximum values, because of course the instantaneous values are going to vary between these maxes and 0. Okay, and it's going to be with sine of phi equaling the voltage across the resistor over the total voltage, and cosine of phi. Okay, and that's because we are representing we're representing the phase angle as phi. That's what denoted has been reserved as. And then the voltage across the inductor minus the voltage across the capacitor divided by the total voltage of the circuit would be cosine. Okay, we have, actually I've switched my trig functions. That first one should be cosine because that's the adjacent side, and then the opposite side is this one. Okay, and I'm just pointing that out to find which angle it is. All right, so let's add it to the picture. So phi right there is our phase angle. Okay. And if you're wondering where does omega t show up, well, omega t would be theta, the same theta that showed up when we talked about generators and motors, because that's the actual theta, that's the time-dependent angle. It's the rotating, alternating part of the circuit. Okay, whereas this phi does not have to do with the alternating part of the circuit. It doesn't have to do with the external driving frequency, but instead, phi is determined entirely by the material properties and geometry of the inductor, the capacitor, and the resistor. But here's the thing, that's not entirely true, because it turns out that the material properties don't tell the whole story for the inductor and the capacitor, because their reactance, and this was a big part of the first half of this lecture, their reactance is frequency dependent. So then it turns out that the phase angle depends on material properties of the inductor, the capacitor, and the resistor, and the frequency. So then we'll say that it is determined by, this is in other words how you would calculate it, by the material properties of R, L, and C, and the frequency. And the frequency of the RC current. Oops. So the AC current. I said RC, but I meant to say AC current. All right, so determined by the material properties of the resistor, the inductor, and the capacitor, and the frequency of the AC current. And that's because the reactance of the inductor and the reactance of the capacitor are frequency dependent, even though the inductance of the inductor and the capacitance of the capacitor are not frequency dependent. But I'll remind you the formula is that reactance is calculated by inductance plus frequency, or combined with frequency. Likewise, in the reactance of the capacitor is combined with the capacitance of the capacitor and the frequency. All right, so last thing here, we have the idea of the power factor, and the power factor is going to be equal to cosine of theta, and what it represents is the sort of how the phase angle is affecting the average power output of the circuit. Okay, so let's get a good definition for that. All right. Yep. So it is defined as cosine of phi. So cosine of phi is just going to be the angle between so cosine of phi is just defined up above, where it's just the voltage across the resistor and the total voltage, and then its value affects the average power output. So average power output of the circuit. Okay. All right. So that is our introduction to our